This is part 3 of trigonometric functions. This one deals with data sets, so more like a real world situation where you just collect data and then you have to model it. So this one has to do with the depth of water, so that's D in meters, in a harbor, with respect to time, which is capital T, in hours. Okay, so they've got this data here for you, and they want you to show that first they want you to plot the data set. Now you can do this on your calculator, but it's in a sense it's kind of pointless because you're gonna have to do it on paper to show them. So what you do is you take a look at what your x is and what your y is. So in this case, if you think about it, time is going to be on the x-axis and this is going to be on your y-axis. Okay, so make sure that you set up a scale that works. So I need to go from 0 to 12, so on the x-axis, and the depth of my water here, so let me move it up a little bit so I give myself as much space as I can. So there's going to be no negatives here, so this could be my origin and that'll be my 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Of course, you would be doing this with your ruler. 1, 2, 3, 4, 5, 6. There. You can fill it all in if you want. And then the depth here, it goes, what's the low? 4, climbing all the way to 10. So I'll probably just go on a scale of from here 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So I'll make a little axis here. I'll make a little axis here using my ruler. Very nice. I'm going to show what these things are. So this is depth, D, in meters. Try to make it a habit to kind of write down what these things are. And this is going to be time, T, in hours. So units and what it is, like that. Okay? And then I'm just going to plot it out. So it's a bit of a task, but there you go. By the way, I didn't mark this down. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at 0, 10, right here, make the points nice and visible. And then 1, 9.68. And then 2, 8.55. And then 3 is 7. And then 4 is 5.45. 5 is 4.32. And 6 is 4. And then 7 is 4.32. 5.45. 7. Then 8.55. 9.68. And then finally 10.1. Right? So consider the data plotted. Now, you'll have to do this eventually, so you can kind of just help you visualize. Draw a curve on that, try to make it nice and smooth and kind of fit your data as best you can. Smoothness is important. You don't have to hit every dot. There you go. That's what it looks like. So, what does it look like? Well, it's sinusoidal, which means that it takes the form of a sine or a cosine function. Show that this is sinusoidal function models this data. That's kind of a way of saying, write down the equation of this thing. So now we're going to approach it just like we did yesterday. So what we're going to do is find the maximum, minimum, and That'll give us everything we need for A and D. And then for B, that letter B, we need to know what the period is. So, a few things. So what am I referring to here? So this will be the form of D is your Y with respect to time is equal to A. Now, is this sine or cosine? Give you a moment on that. It's cosine because you're starting at a maximum. So cosine bx, oh, sorry, not x, it's bt, right, plus d. Now we need to find these values. Once we have these values, we have the model. So I hope you know how to do that by now, based on yesterday's class. So how will I find A? A is equal to the max value minus the minimum value of y divided by 2. So in this case, it's going to be 10 minus 4 divided by 2. So it's going to be 3. Okay? So that's one down. 2. Let's get D. I always like D because it's fairly straightforward. That's going to be max plus min divided by 2. And that's going to be 10 plus 4 divided by 2, so that's going to be 7. And last but not least is B. B, remember, has to do with the period. So how far do I have to go along the x-axis before this pattern starts to repeat? I dare say it'll be 12. So it'll be 360 degrees divided by 12, which is equal to, I cannot think, 30. Okay? So we've got all three of our values there. 1, 2, 3. So that means that dt is equal to 3 cosine 30t plus 7. And there it is. Let's give it a good, nice, bright color. Nice. Okay, so that's B, and I'll show you in a separate video how to check that on your calculator. C, Sam's boat needs the water to be at least 6 meters deep in order for it to safely enter the harbor. Predict the range of hours between which he can sail in and out of the harbor. If your graph is good, you can do this straight from the graph. If it's bad, you can graph the equation on a calculator and figure this out. But think for a moment what you're doing. If you're hearing screaming and laughing and idiocy, those are called neighbors. That's what you guys sound like in a teacher's house. So if ever you think about that. So back to the problem. Sam's boat needs to be the water at least 6 meters deep. So I need to be at least this deep. Right? Yeah, I've got to be at least this deep for me to be able to sail. So when can I sail? Well, this will be the cutoff time, here and here. Okay, so it just happens to fall very nicely. Otherwise, you can estimate it from your graph, or like I said, you can use your calculator. But when is it? How do you write that? The range of time for me that it is deeper than 6 meters is when t is less than what is that? 3:30? So 3.5 hours, but I will say 3 hours and 30 minutes. That's 3.5 hours, right? So I'm reading kind of this. And I want this also, which is 8.5. So it's when it's less than, before 3:30, right? Maybe I can write it in a nice, normal human being way and say 3:30. Or when t is greater than 8:30. Right? So there you go. There you go. So that's it for that question, and I'll move on to the second one. I'm just going to do two. Here's another data set. This one, notice the numbers are kind of nasty. There's scientific notation. It's not the end of the world, but it's a little bit of a pain. So I'm going to change this a little bit. I'm going to actually do time here. Instead of seconds, I'm going to do it in 10 to the negative 4 seconds. So what that means is I'm actually just going to graph here 1.5, 3, 4.5, 6, 7.5, 9, and this one you might have to kind of try like what will that be? 1, 2, 3, 4, 10.5, 12, and 13.5. And I'm going to do that. And when I answer a question, if it's time, I'll just kind of add in the times 10 to the negative 4 back in. That's how you can do it. It just saves you a little bit of time. Those numbers are not nice, okay? But it is what it is. So if I look at this one and find a model for this, well, at least they didn't ask me to graph it, okay? So I'm going to graph, all right, I'm going to find a model for this thing using the function of this form. Okay, so they want this, a sine bx plus d, okay? And they say, by the way, use technology to plot the data set. It's nice, but I'm not, on an exam, they couldn't make you do that because how would they know? You may have to do it, but it's there's no real point to it. Anyway, so back to that. So how do we find usual story? How do we find these three things? Same thing, we got to find what's our maximum, what's our minimum. So A is equal to max minus min divided by 2. So in this case, what is my maximum value? And by the way, which one's x, which one's y? So that's x, that's y. So I'm looking for my maximum value of y. So what's that going to be? It sure looks like it is 0.9961. Okay? Now, it's not going to be perfect what I'm going to find because I don't think that's my actual maximum. That's just one of the points. So 0.9961 minus my minimum, what's my lowest value? Negative 0.5569, something like that, divided by 2. So that's equal to, use my calculator, so 0.7765 according to me. So that'll be the amplitude. And D is max plus min. Did I do it in reverse? No. Max plus min divided by 2. That's right. So it'll be the same numbers. Right? So it'll be that again. So if you hear swearing, I apologize. Again, that's my neighbors. That is what we hear. D, and then last but not least is B. Now B here, let's see. How long does it take for this pattern to repeat? You might be looking like, it's hard to tell. I start at here. I start at 0.4. Then it's slowly going up, 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 down, down. So maybe it was good to use technology. And then down, but notice I go past 0.4 and then down some more. It's not even a complete picture, right? This is a little tough to tell. So what can I do for this here? There's a sound wave. What will I do? I will go for, because remember, this is a sine wave, and it's going to go something like this, right? So where am I on this? Well, I'm going to look for, if I start here, I'm going to look for this point. I'm going to think about that. So if I started here at around 0.4, is that my midpoint? Not really. Golly. I might just go for the calculator on this one and show you how to do it completely by calculator. But let's try to avoid that temptation. It's just too easy. This I can clearly see is kind of, there's a maximum right around here, roughly, at this time. And what I'm looking at is these values here. This A is the amplitude, and this is that kind of midpoint. So that midpoint, that D, would be kind of, this would be where this would be, 0.2196. So I'm kind of hoping to see something like that. When did that happen? Oh, I missed a point, 0. So it happened somewhere. The 0.2196 is happened somewhere here. So the time would have been 0.75 times 10 to the negative 4. Don't forget that times 10 to the negative 4. And the where's the next one like that? Where's the next point where it's roughly at that value? And I'd say it's about 10.5. So this is, it goes between here all the way to here to 10.5 times 10 to the negative 4 is, gets me from here to here. So those are those times. Now that's not a full period. That's only half of a period, so I'll have to double it. So let's see, what's the difference between those two numbers? 10.5 times 10 to the negative 4 minus 0.75 times 10 to the negative 4 will give me 9.75 times 10 to the negative 4. And then I'm going to have to double this. So 19.5 times 10 to the negative 4. This is not good scientific notation, by the way. But this will be my period. So what's B going to be? It's going to be 360 degrees divided by 19.5 times 10 to the negative 4. That's what it's going to be. Whew. That was a little bit of work. So I get this to be 184,615. That's what's B going to be. So I finally got it. Whew. That was a tough one. Hope I got it right. So the equation will be 0.7765 times sine to 184615, and you could write that in scientific notation if you feel like it, plus 0.2196. Okay, that number is really big, the B, but it makes sense because usually you go from 0 to 360, this one is going into very, very small kind of values for x, so it's a very small difference. So it makes sense that that would be a very large number. And that is, what did they use, just y? Fine. So that's what they have here for the equation. And then they say, hence, predict the decibels of the sound after 0.00011 seconds. So for part C, I would replace x with 0.00011 seconds. Right? And I'll let you do that. I'm already kind of finished with this question. And D, hence predict the decibels after 0.2. 0. So I would do the same. X equals 0.002 seconds. And that'd be pretty straightforward. E is a little bit interesting. Comment on which of your answers, C and D, are more reliable, given a reason for your answer. Well, which one of those two would be more reliable and why? Give you a moment to think about that. But C is more reliable. Because it is interpolation, because it's within your data set. Whereas D is less reliable because it is a case of extrapolation. If you remember that. If not, look it up. I'm going to stop here and I'll throw in another video looking at this stuff with a calculator.